Hello, Chem 2. Today, what we're going to do is discuss the concepts that are going to be overarching in the Thermochemistry Chapter 8. Hopefully, everybody is safe and healthy. This is going to feel really, really weird to me. I just got done talking to you guys online not even 20 minutes ago, and I'm going to find myself repeating myself a little bit too much. So if you find this to be a repeat, there's a reason. There's a lot of stuff that I talked about in the Flex Hour that I'm going to discuss here on this PowerPoint. Going to try to go over all the basic concepts that are a part of thermochemistry to the best of the ability, touch on a little bit of math towards the end, but try to cover what all the information is in section 1. So first thing, administrative pieces. Chapter 5, gas law exam is online. I think I gave you a week to get that done. So please take care of that. Should be really, really easy in order to pass that. I say that easy because you have multiple opportunities. If it doesn't go well for you, just do it again. I think I try to make it 5 total attempts. Also, this chapter is chapter 8, as you saw on the last slide. So there are 2 owls there. There's the required and the optional. The required is the one that's going to go into the grade book. So how does this chapter relate to others? Well, we're going to be focusing on energy. Reactions, when they occur, the reactants will become products, but another thing that is involved in the entire reaction is energy. Energy being lost, energy being gained, energy being absorbed, energy being released, but energy is also a part of it. So that's what this particular chapter is all about, is about the energy involved in different chemical reactions. We are not going to cover these last 2 bullet points under key concepts. We're not going to deal with the 2 that have delta E's in them. We may address them in very, very overarching terms, but for the most part, we're going to focus on this delta H concept and what is thermochemistry and what is this Q concept. So that's what we're going to do. Today, I'm going to talk about heat flow and specific heat, what is M and what is delta T, and how to do those calculations before we use the heck out of them with the next 2 sections of section 2 and section 3. So chapter 8, broken into sections. We're not going to talk about sections 6 or 7. I'm going to have to save something for AP Chem, but we'll deal with those a little bit later on if you guys come to see me in AP Chem. So section 1 is principles of heat flow. So this particular chapter revolves around heat, energy, and heat. In Chem 1, you briefly discussed the difference between heat and temperature. Well, now we're going to focus on the difference between energy and heat. Energy is the capacity to do work. How that work is done is either in terms of heat energy or mechanical energy or light energy or physical movement. Something is going to happen. That's what energy is, the ability to turn energy into some other form of energy, mechanical, heat, whatever. Heat is a very, very specific form of energy. And actually, we are in a situation where we really want to make sure that all of our reactions avoid having other types of energy. We do not want to have a reaction that releases a whole lot of work and explodes. We do not want to have a reaction that releases a whole lot of light that we can't measure accurately. So we're going to try to make sure our reactions in our descriptions are ones that we can quantify and clearly label between amount of energy lost and amount of energy gained via the system. That is what thermochemistry is the study of that heat flow that goes along with the chemical reactions. Chemistry, the chemical reactions part, thermo, the heat. So energy is always going to move from a hot object to a cold object. More specifically, that heat is always going to move from a system that has a high amount of energy to a low amount of energy. When you open up a door during the winter time, it's going to feel cold. Well, that's because the energy that's in your room is going to be leaving your room and going outside, because that energy wants to go from a high amount of energy inside to a lower amount of energy outside. Vice versa, on a nice sweltering hot summer day, and you have your energy AC cranking in your house and you open up the door, you're going to feel this waft of heat coming at you. That's because that energy is going to be coming from the outside into your house. Energy is always going to move from a high energy to a low energy. We're going to use the symbol Q for quantity of heat to specify the amount of heat that is going to be transferred. And that Q is either going to be positive or negative. We'll talk about what that means in a second. But in order to understand the quantity heat, Q is the quantity of heat. The other part is which direction does it go? Does the energy go from the system to the surroundings, or does it go from the surroundings to the system? Well, what is the system and surroundings? System is the part that we're worried about. In the case of chemical reactions and thermochemistry, it's going to be the chemical reaction. Does that chemical reaction release energy, or does that chemical reaction absorb energy? The example that I use a lot in the Flex chat is a piece of wood burning. That piece of wood burning is going through a chemical reaction. The wood is reacting with the oxygen in the air and creating carbon dioxide, water, some carbon soot, all kinds of other random products, but there's a chemical reaction taking place. That chemical reaction is losing energy. The molecules are losing energy. How do I know that? It feels hot around it. That piece of wood did not feel hot, but when that piece of wood reacts, it releases a lot of energy to the surroundings. I can feel it by standing around the campfire, standing around the bonfire. Okay. So for instance, the example here is talking about what is the system and what is surroundings. Well, if the system is the water, in the case of a hot plate being turned on, the water is going to absorb heat. That is an endothermic process. As soon as you turn off the heat, turn off the hot plate, then the water is going to lose energy and the system is going to be losing energy as the temperature in the water decreases. How do we quantify the amount of heat lost or gained? Well, we're going to use this concept of a state property and a change in a state property, whether it be a change in heat or a change in enthalpy or a change in temperature. We're going to be talking about different changes that take place. Delta is the symbol that's used for change. And delta will always be change in terms of what is it now versus what did it used to be. What is it now, final, the x final, the property final, minus what it used to be. We're going to be looking at things like delta T, delta change in temperature. What is it now versus what it used to be. So suppose I'm sitting here at the Fahrenheit household and it feels chilly around the house and it's hovering at a solid 63 degrees Fahrenheit. And I turn on the heat and I wait about an hour. Now inside the house, it is, instead of being 63, it is 72. We have a change in heat that is 9 degrees. Now, is that 9 degrees positive or 9 degrees negative? Well, let's think about it. Change in temperature would be final temperature minus initial temperature. Final temperature was 672. The initial temperature was 63. 72 minus 63 is a positive 9 degrees. So the change in temperature, the delta T, would be a positive 9 degrees. So when talking about delta, it's always final minus initial, and we're going to be seeing that a lot. Final minus initial, final minus initial, final minus initial. We're going to use it a ton, whether it be the final amount of enthalpy, final amount of entropy, final amount of energy, final amount of temperature, minus the initial conditions. 3, 2, 1. Let's try to start this again. So we're going to use the symbol Q. Q is the energy transfer, the amount of energy transferred, and the symbol is the positive or negative tells you whether or not it is going to be which direction it's going to go. So when we're talking about heat, there's two parts to it. There's the quantity, how much heat is being transferred, but also second is what direction does the heat go. So in the case of an endothermic process, and the example that they use here is water melting, solid water becoming liquid water, water is melting. What's happening to the energy in the system? Well, as the solid water becomes liquid water, the molecules move more and more. And in some cases, the water is actually going to increase in temperature. That is going to mean that the water is going to absorb energy. So there's a certain amount of energy that goes in, a certain amount of heat that goes in, but since it's going into the system is increasing in amount of energy, that is going to be a positive Q. Vice versa, if you have a reaction here, they have methane gas reacting with oxygen. When methane gas reacts with oxygen, that's kind of what happens in the Bunsen burners. You make carbon dioxide and water, that's a combustion reaction. We've seen those before. Then that's going to have a loss of energy. How can we tell? Well, it gets hot. But the loss of energy says that there's going to be some quantity of energy, but since you're going to have a negative number, which means the system lost energy. The system lost energy. So there's the two examples, ice melting and a Bunsen burning or heating. In the case of ice melting, energy comes into the system. In the case of a Bunsen burner, the energy leaves the system. So let's talk about direction. So positive is energy in, positive is work in, negative is energy out, negative is work out. Heat is either going to be released or work is going to be done to the surroundings. So that leads to what kind of numbers or what kind of quantification are we going to have? Well, we're going to use 2/3 different units of measurement for energy. One is the calorie. And we'll talk a lot more about what a calorie is tomorrow, but you've probably heard about a calorie because they're associated with food. There's a certain amount of calories you're supposed to consume in a day. There's a certain amount of calories on every piece of food. There's some caloric quantity. That calorie is associated with energy. How much food you eat gives you how much energy you're going to consume and how much energy your body has to break down. Now, bizarre little twist, the food calorie is a kilocalorie. The food calorie is a kilocalorie. The calorie, by definition, is 4.184 joules. Or more specifically, a calorie, by definition, is the amount of energy that's needed to change 1 gram of water, 1 degree Celsius. 1 gram of water, 1 degree Celsius. And a joule is the kilograms times meter squared per second squared. It's a unit of measurement, much like the Newton or the meter or the second. It's a unit of measurement. It's just used to measure energy. So the calorimetry equation, there's two of them, and we're going to use these a lot. I want to just touch on them very, very briefly here, and then we're going to use them a ton tomorrow. There's two different ones. There's one that talks about what happens, the heat capacity, and another one that focuses on the specific heat. Heat capacity. While a system is undergoing a phase change, or better yet, while a system, you don't know how much of the material you have, you just know that system has a ratio of amount of heat that's needed to raise the temperature 1 degree Celsius, a ratio of heat in or heat out versus temperature change, then you would use this concept of heat capacity. An example might be if I had a block of metal and I knew that I had to put 1,000 joules of energy into that piece of metal to make it increase 10 degrees, I would have a heat capacity of 1,000 divided by 10, 100 joules per degree Celsius. That's the heat capacity. Do I know how big that piece of metal is? No, I don't care. Do I know what that piece of metal is made out of? No, I don't care. I just know that piece of metal requires a certain amount of energy to go into it to make it change 1 degree Celsius. If that information is what's given to me as a heat capacity, then it's pretty simple. If I know I have a ratio of heat per degree Celsius, I'm going to multiply times the change in temperature to find out how much heat went into it. So if I take that same block of metal that has 100 joules per degree Celsius, and I know that it increased in temperature 10 degrees Celsius, I know that I had 100 times 10 or 1,000 joules of energy went in. Well, another thing that we're going to use a lot more, and I mean a ton more, is the concept of specific heat. And that's where every substance has a amount of heat that's required to make it change its temperature 1 degree Celsius, but more specifically, the amount of heat that's needed to raise 1 gram of that pure substance 1 degree Celsius. So and it depends on the identity, the phase. There's water's solid heat, specific heat is different than liquid specific heat, is different than steam specific heat. They're all very, very different. So there's a very specific, no pun intended, number that's associated with each type or phase. If that's the case, then you're going to take the mass times the specific heat times the change in temperature to get the quantity of heat. And again, these two equations, we're going to use a ton with tomorrow's PowerPoint, but I just want to introduce them. And the last one that's associated is called the molar heat capacity. And that's if instead of doing the amount of energy is needed to change 1 gram of material, you have a number for 1 mole. The reality is you have a relationship that there's going to be units here. There's going to be a number. Our number we're going to use for water is 4.184 joules per gram degree Celsius. If it was per mole, it'd be a different number, and this unit, for instead of being grads, would be in moles. Just make sure your units cancel out. Sig figs and dimensional analysis are your friend. Here's some different substances showing you the different specific heats. Like I said, they're all over the place. You'd have to be given them, except for the one, water's specific heat. Water's liquid specific heat, 4.184 is a number that you should memorize. So let's see how you would use this. It says compare the amount of heat given off by 1 mole of liquid water when it cools from 100 to 30 to that given off when 1 mole of steam cools from 200 to 110. Now let's look at this. First thing, the liquid water dropped 70 degrees and the steam dropped 90 degrees. So they're different, but since they're not the same material, you're not necessarily going to have the same straight up relationship between temperature and energy. You have to see for each one how much it takes. So if I go in and I look up some numbers, I know that I have 1.4 moles of each. I have final temperatures were given to me, initial temperatures. I need to go in and determine how much the Q is for each one of the substances by doing a little bit of math. Now the C for steam is 1.187 and the C for water is 4.184. So the numbers are different. You'll notice that water has a really large specific heat, and that's kind of cool. It's kind of an interesting fact, but water has a very, very high specific heat. So you should know that delta T is final temperature minus initial temperature. So these things are both getting cooler, so they're both going to be releasing heat. So if I take for liquid water, final minus initial, 30 minus 100 is a negative 70. It released energy. It got cooler. Okay, so convert my grams to moles. Okay, so I got 25 grams. So my C for liquid water is 4.184. If I'm going to get my Q, it's 22.5 times 4.184 times negative 70 is being my number. And so therefore, let me move my little counter here. I get negative 7,370 joules of energy, or 7.37 kilojoules of energy lost. The water lost energy. Of course, it got cooler. What about the steam? Well, for steam, I have the change in temperature being 90 degrees. It's more, it loses more energy. My mass is the same because I have the same number of moles. But now my C is a lot smaller. Instead of being 4.184, it's only 1.87. It is a lot smaller. So if I do my math, Q equals MC delta T, I get that my energy is 4,240 joules of energy. There's actually less energy lost in having steam drop 90 degrees than it is for having water dropping 70 degrees. So the liquid water dropping 70 degrees actually lost more energy compared to steam 90. And that's mostly because the specific heat of water is significantly greater than the specific heat of steam. So what does that mean? Well, first off, the fact that both of them have negative values means that the heat was lost to the surroundings. The heat left the system. And then don't connect directly your temperature to the amount of heat lost, especially if you're talking about different materials, even in terms of phases. Just be careful making sure you use the correct cues. So what's next? Next video, we're going to talk about measurement, a lot more measurement in regard to heat flow and calorimetry. The next video might be a little bit longer. It's going to be a little deeper, or we're going to talk a lot more about the different types of calorimetry and the different ways to measure energy. Hopefully everybody is being safe, being healthy, practicing your social distancing, and you guys have a great day. I will see you tomorrow in the next video. Always remember, never forget, sig figs do matter. Have a good day. Toodles.